Okay, pallet coupling. Okay, great. So as I mentioned, Substrate believes in building this modular composable blockchain runtime, right? With all these different individual components. These building blocks are in Frame are called pallets, and pallet coupling will basically teach you how you can configure them to interact with each other, right? You can imagine if you can't interact with them, you can't actually compose complex or interesting ideas, right? The whole pallet story doesn't work. So with this pallet coupling idea, you can really think of these pallets as like applications. And when you're building your blockchain, you can pick the specific applications you want, put them together, and make it work to a cohesive end-to-end story, okay? So there's two main types of coupling. By the way, when I say coupling here, this is not really a frame thing. This is just Rust. Like, we're just figuring out how we have two different Rust crates talk to each other, right? But there are different ways we can do it using the Rust practices. So this isn't like frame we built in coupling. This is just Rust. But but how you do this stuff in the context of frame is relevant, right? So the first one is tightly coupled pallets. These are pallets which are directly connected to one another. So when you construct your runtime, if you have two tightly coupled pallets, you must include both of them, right? You must exactly have this crate and this crate, right? It's not like optional. You must use both of them together. They're tightly coupled, etc. Then you have loosely coupled pallets. These are pallets that are connected loosely with a trait or interface, right? This is what Rust provides. And in this context, you can basically substitute the coupling between two pallets with any pallets which support the interface. So in this context, you can imagine that I have a pallet which has an interface to access balances of the user. It could be that you use the balances palette for that, or it could be that you create your own palette, which also satisfies those interfaces, and use that instead. In this case, this one palette could interface with both of them, or either of them, of your choice, right? But this is defined by traits and interfaces, versus directly connecting the crates together, okay? And then we'll go into the details about these more. So what does a tightly coupled pallet look like, and why do we use it? Well, first, tight coupling is generally easier, but less flexible, right? So it is something that, I would say, as a process, if you're going out there and you're building a new blockchain, you just start with tight coupling. It's easy. It doesn't have any question marks. You have to think about building interfaces. You just make it work, and then you would later refactor and actually maybe create some interfaces and some loose coupling. But it's faster, it's easier, but it's of course less flexible. Of course, if you tie two pallets together, you're basically saying you must use both, right? And it looks like this. So again, this isn't frame. This is Rust. You have a public trait. We have this configuration trait, which we mentioned all pallets have, and we'll go more into that, in time. And you can see here that, as I mentioned yesterday, every single pallet that you create in frame assumes you have access to frame system, right? That is tight coupling. We have in every single pallet. You'll see in your code too, that you always have this, your trait config inherits from frame system config. But you can also add other pallets, like pallet treasury config. So in this context, this is all tight coupling. And again, frame system here and pallet treasury here, these are crates, right? So in this context, you cannot compile this pallet without having these crates imported into your system, right? And again, this is not frame specific. This is just the use of inheritance inside of Rust. Okay. And yeah, and like I said, note that everything is tightly coupled frame system. So as I mentioned, you cannot build a frame palette without using frame system. That's because everything is tightly coupled to it. And we have, like, in our macros, we assume that frame system exists, right? Okay, so that's what it looks like. What does it mean? So if pallet A is tightly coupled to pallet B, then it means this pallet A requires a runtime which is also configured with pallet B. Okay? Now, I hope I didn't mislead anyone with the words I'm using. You can use pallet B without pallet A, because pallet B might not be tightly coupled to pallet A. But if pallet A is tightly coupled to pallet B, if you include A, you must include B, right? Yeah, that's the last part right here. By the way, I think you cannot. Can you? I think you cannot tightly couple both directions, because I think Rust does not allow you to do cyclic dependencies. I'm pretty sure that's correct. So you can only really, tightly couple one direction. Okay. So an example, as I gave here, is a treasury palette, actually. So who here has interacted with the treasury from Polkadot, or at least knows about it, right? Yeah. So the treasury pallet is actually using the tight coupling to add additional features. So the treasury pallet, the base pallet, is a standalone pallet which controls a pot of funds where governance can actually go distribute those funds and help support the network, pay for developers, pay for things like the PBA is supported by the treasury, right? Now there are other pallets which are tightly coupled to the treasury. These things called tips and bounties. These things actually also exist. These are basically like extensions of the treasury pallet, other ways that we can actually use the same funds. So the treasury sets up a single pot. It has a basic method of making proposals, but then there are these other tightly coupled pallets, tips and bounties, which have like more complex logic for how to access the same funds, right? So we're not making multiple treasuries. We still have one treasury, but we have multiple interfaces which we can access. And in terms of like UI, UX, you can really think that this is all, when exposed to the user, kind of one story. It's not like there's a treasury palette and a tips palette. It's like there's all one interface that you can do tips, and you can do treasury proposals, you can do bounties. That's all part of the system. But again, it doesn't make sense to recreate a brand new pot for tip or a brand new pot for bounties. You basically, can just take advantage and extend the treasury palette. So this is directly what it looks like. So the pallet treasury, and we can look at this when we go through the pallets today. Its config trait is just accessing frame system, right? But something like pallet tips and pallet bounties, its config trait is accessing frame system and pallet treasury. And that means basically you directly have access to all of the functions, all of the storage, all of the things from treasury without having to do anything. You just get access to it directly, just like you would access any public struct, any public function from another crate. Yeah, it means inheritance. It's exactly that. Yeah, I'm not sure if Russ used the words inheritance. There might be a different word for it, but it's basically that. Yeah. And yeah, okay. So then this is the kind of error you would see if you try to use a tightly coupled pallet without the main one. So if I try to use bounties without including treasury, I'm gonna get an error like this. It's gonna say that the trait bound pallet treasury is not satisfied, right? That we have required in bounties that you must have this trait satisfied, and we haven't satisfied it. So it's a very actually straightforward error from Russ saying, hey, you're missing something you told me we must have, right? Now again, the advantage of tight coupling is that you just get direct access. It's just basically importing a crate, any public function, any public struct, any storage item, like stuff, you just directly get access to it. You can directly manipulate it in however way you want, right? And so it's, like here, when you're accessing the block number from frame system, you're just directly calling into the pallet, calling some public function, right? What else here? When you're doing things like ensure signed, again, there's a comment about this last night. Someone remind me to talk about that. But this is a public function being exposed from frame systems. You just get access to the function, right? And then even here, inside of the bounties palette, I can actually emit errors from the treasury palette. So I can take a treasury error and emit it through my palette, because the errors are also just public. It's a public enum. So it could be that if my bounty can detect some error, I might not want to show it as a bounty error, but as a treasury error. And I can do that, right? So again, tight coupling makes sense when you want to break apart a single large pallet into smaller yet fully dependent pieces, right? We could have made one big treasury pallet with tips and bounties and all this kind of stuff in it. But imagine that you wanted to import the treasury pallet, but you didn't want bounties, right? If you made it all one big crate, you would basically force users to all import everything, right? In this context, you can think of them as extensions. Like, here's the main thing. Here are direct extensions of this pallet. You can pick the level of granularity you want, right? So you can break things apart. But remember, there's less flexibility in how you can configure these tightly coupled pallets. Basically, once you do tight coupling, you don't have the flexibility, for example, to go in and create your own version of an extension and plug it in. You might have to modify the source code or fork some code. So this is where loose coupling is a better solution when you're trying to do more. Try to create pallets which are more open to the community to modify and change and to extend. Okay, let's pause there. Any questions about tight coupling? Please.
So I have a question. Can you go back to the 7th slide?
7th slide. 7.
So on this slide, we connected the pallet treasury, right? Using just frame system. Here we connected tips and bounties, right?
So this is the code for Pallet Treasury, and it doesn't have any tight coupling, so except for frame system, which everyone has. This is what the Pallet bounties and Pallet tips looks like, and it is tightly coupled to Pallet Treasury.
Okay.
Yeah, and I mean, let's just spend 1 second. We just spend 1 second. We look at the code base.
Just the naming that Pallet Treasury is in frame.
Yep. So here, this is Polkadot SDK. Actually, I need to make it bigger for you guys, right? This is the Polkadot SDK. In Polkadot SDK, there's a folder substrate. In the folder substrate, there is a folder frame. In folder frame, you'll find many pallets, right? You'll also find things like executive, which we talked about is not a pallet, but it's some logical code. You'll also find things like support. These are like libraries and traits and other stuff. But most of these are pallets. So if I look at Pallet Treasury, this is the pallet right here, and I look at this, you're going to see a basic pallet. Where's my X? There we go, X. You're going to see a basic pallet. If I walk through this, I'm going to see a struct pallet, right, from the template. I'm going to see the trait config. I'm going to see pallet : storage. I'm going to see pallet : call. So it's just a pallet, right? It's the same thing that you guys built yesterday. But if we look at this config, you can see here it's implemented config frame system. And this every single pallet will have this tight coupling. So all of your templates, everything will have this. Now quickly, let's look at the bounties palette. This is a different one. And you can see here, if I go to the pallet config, it has frame system and Pallet Treasury. So what I'm trying to say here is that this second pallet, the second folder, the second crate, is directly dependent on their existing treasury palette. So you cannot have one without the other. Yeah, please.
So my apologies here. I just came in regards to just again lost, but just looking through the actual code alone, it seems like these couple pallets are more or less just like class inheritance, more or less.
That's exactly what I've been saying. It's just inheritance.
Yeah.
So both tight coupling and loose coupling is not a frame thing. It's just a Rust thing. These are just terms we're using in the context of designing pallets together. Yeah.
Right. And comparing to back to Swift, which I know really deeply, these are kind of like what they have for protocols, where you basically just define a set of functions within the actual protocol itself, and then you have the actual inherited class to find those functions and variables, more or less.
Mm-hmm. Yeah.
Yeah, that's just more or less how I basically more or less compare it to pallet coupling, more or less.
Sure. Yeah. Okay. Okay. Any other questions about tight coupling here? Okay. So let's show you the better solution, which is loose coupling. So loose coupling, and this is what most of the pallets that we have in frame, they all basically use loose coupling. I mean, obviously treasury pallet is one example that doesn't, but things like the balances pallet, things like the governance pallets we have, all of them are using loose coupling. And they're taking advantage of the fact of creating an interface that allows you to access a pallet without defining that you need to access this specific pallet, right? Again, if you define the interface, any crate which satisfies the interface could satisfy the extension that you need for your pallet, right? And it's the preferred way. So again, as a developer, I think it makes sense. Usually, you make a super pallet, then you break it into two tightly coupled pallets, and then you define the interfaces and then make two loosely coupled pallets. That's like a very natural story for how you quickly can write code, right? It's very hard, for example, before you've written any code to like think, this is exactly the interface I want, unless you're like a spec writer or whatever, right? I'm more of a hack as you go kind of person. But anyway, so when you want to do loosely coupled pallets, basically, you're able to emphasize the fact that you can create pieces of logic that anyone could extend or anyone could modify and create a much more extensive universe of pallets. And it kind of looks like this. So again, we're back in the config, but we're not using the inheritance. We're using actually configurable associated types inside of the config. And these associated types have traits which are defined, that are required to be implemented. And basically, then you can go use them inside of your pallet. So here you can see the pallet requires some associated type, native balance. Native balance is configured that it must implement the inspect trait and the mutate trait. However, there's no requirement on where these traits are coming from. There's no requirement that it must be this crate. Any crate or struct or object you create that implements this interface could satisfy this requirement, right? And this is exactly how you access things like balances inside of Substrate. Sure, we can do that in live coding. You just remind me. But here we go. So as I mentioned, to begin loose coupling, first thing you do is define a new trait. So usually these are defined in a tertiary crate. So I have pallet A, I have pallet B. Usually you don't want to define the trait in either of these pallets, because if you define it in one of the pallets, you require that you import that pallet to access that trait. That's back to loose tight coupling. So normally you have a third crate, which is like a support crate, which defines a bunch of your common traits in your interfaces, right? And that's actually what we do in Substrate as well, right? But you create this like kind of supporting crate. These are all the ideas of that are expose just traits and structs and stuff like that, right? So here is the inspect trait. You can see there's a type balance, and then there's a bunch of functions like total issuance, native active total issuance. Probably there's going to be transfer down here. There's a bunch of things that you can do to access this function, right? And then inside of your pallet or whatever pallet you create, you can then implement that trait, right? So inside of pallet balances, we actually implement the inspect trait for the pallet struct, right? And we actually just define, okay, well, total issuance, I'm going to read the storage of total issuance and return that to you. I'm going to do some math, saturating sub, and return it to you. So I'm actually just taking, like, again, the pallet has storage, it has logic in it. I can just directly access that storage and logic and then expose access to it through these interfaces, right? And again, the idea here is that this exact interface, you could write your own pallet, implement this interface, and it would still work. So anyone could implement this interface, right? Finally, now you have basically the ability to depend on this trait. So as I mentioned already, you have the trait which wants to use another pallet. It defines in its config this associated type and the required traits it needs. And then inside of the functions in your pallet, you can actually use directly these functions, right? So because inside of my pallet there's a native balance associated type with these traits, I can then in my own code write T : native balance : transfer, right? Because this is the function that's exposed by this associated type. And again, I'm accessing some unknown type. We don't know yet what this is going to call, but we know that we can call it, right? The last piece of the puzzle is actually defining what are we going to call. What is actually implementing this interface, right? So inside of your runtime, you will go and you will actually configure your pallet. You'll actually define concretely, I want to use this type, this. And you might say for native balance, I actually want to use pallet balances. So in this context, this is at the same level of tightly coupling. At this point in your runtime, you have defined which crate exactly you want to use. But the idea is that in your runtime, you could change this crate to a different crate that also implements this interface, right? So in the context of you designing your pallet, you never made an assumption about pallet balances. You only made an assumption about the interface. And here, you're actually able to then define, this is the crate, this is the pallet which implements this interface. Does that make sense? Remember that and this is one of the harder parts for frame development for a lot of new developers. That when you're working inside of a pallet, the best thing to do, and the thing that you'll do often, is work with generic types which are not concretely defined yet. At some point in your runtime, you will actually define these concrete types. You might have in your head, the balance type is U64, so I should be able to add to U64. But because we try to keep everything generic, it's not actually U64. It's some trait that implements into U32 or add to whatever kind of thing. And the runtime defines concretely it's U64 at some point, right? Actually, this reminds me, I need to show you actually some tricks to do. Show you some tricks on how you can actually cheat and make types concrete inside of the runtime, inside of the pallet, if you want to. It's kind of a cheat which is okay to use inside of these things. Let's do that. So how to make types concrete in a pallet. Okay. But yeah. So again, this is the place where things are no longer loosely defined. It's concretely defined what's being interfaced. But you can see that the advantage of this, the advantage that I could basically create another pallet, reconfigure it, much more powerful. Now the challenges of loose coupling. It's obviously difficult. You need to think ahead about interfaces. Interfaces, don't always match exactly what you want to do. Especially if you have to think about interfaces, not just like, oh, I'm gonna make an interface for exactly by pallet. That's basically tight coupling. You need to think about an interface where other people could also implement it themselves, that they would have their own ideas and be able to actually do things in a creative way. It also, usually when you make interfaces, you need to make strong requirements about the complexity of the interface, right? So it can't be that I make a pallet, I loosely couple to some balances. If I use your pallet, the complexity is O of n, and I use another pallet, it's O of n squared. That would be terrible, right? That you can't have, that the logic is not consistent or kind of, it should be expected when I write an interface what the complexity of those functions should be, right? And you need to satisfy those requirements. Yeah. What else do I say? But yeah, when it's done right, it can be very powerful. I mean, ERC20. I'm sure everyone here has heard about that. It's basically that. It's an interface defined that any contract can implement and allows access to things like Uniswap and other exchanges directly through this interface. Like, that is the power of a good interface. You get basically a whole DeFi ecosystem built on just one interface. Okay, and then of course, when you're doing a loose coupling, it can be a little bit difficult because you have to deal with a lot of generic types, right? And this is going to be, again, one of the hard parts. And this is one of the things why I recommend you do that Rust state machine, because I think it allows you to directly play with generic types and the creation of generic types from the ground up, right? But you can see that if I go back real quick, the fungible trait has this generic balance. So when you're using this interface, and this is what you'll all be doing, when you actually use this balances interface, you're going to want to try to directly access this type, and you're going to want to like add numbers to it and stuff like that, but you need to know that this is a generic type. You'll be dealing with generic types throughout. And this is one of the things that we'll teach you to deal with throughout the frame course. But it's challenging. I think it's really kind of a place where a lot of the newer developers, especially for Rust, they start hitting their head on the wall. But again, this is one of those things where I think it's very easy to unblock you. If you're running into a problem around generic types, find me early, find me quickly, and then I'll unblock you. Right? This is not something that's worth struggling over, right? Okay. Any questions about tight and loose coupling? Please, yeah, yeah.
So my question is how complexity of implementation can influence on our connections is. So in runtime we connect implementation according to interface, right?
Mm-hmm.
And you said that if implementation have different complexities like O of n or O of n squared, it actually doesn't matter, right?
No, it does. It does matter. So this will go more into benchmarking and weights. That's kind of later in the conversation. But one thing you should hopefully know that you've learned from the blockchain is that it's very important that these systems are correctly metered. Like I think in the basic contract systems you have gas metering, right? And so when I'm designing a pallet, it needs to be that when I run these functions, because we don't have gas metering, we use something called pre-measured weights. That it needs to be that the weights of my system need to match a complexity of the actual interface below. So it shouldn't be, for example, if I switch someone's pallet, that all of a sudden the complexity is way, way higher. Now, there might be situations where that's okay. It depends, slightly. But at a high level, when I think the best practice is when you define an interface, you should also be defining the level of complexity you expect for that code. That's I think, the best practice.
But from the code point of view, it's okay, eh?
Yeah, and the compiler won't know. This is a developer problem, right?
Okay.
Compiler won't know. Yeah. But that's the thing. Compiler won't know that you made a function and you implemented it as an infinite loop, right? Like there could just be bad interfaces. So again, what I'm talking about is that when you're actually doing loose coupling in an ecosystem of developers where everyone wants to contribute, the best thing for you is to also not only define the interface, but define the complexity of the interface and the things that you considered about that interface, right? Yeah.
Do you expect that in our assignment that we define complexity?
I think that the Dex palette, I ask you to create an interface for swapping the thing, and it's a super simple. It's again 5 lines of code. But that basically is a loose coupled interface. Any other questions? Okay, nice and short. We're doing easy. Let's just jump into the next one. So I'm going to, so I think this is the best idea. I'm going to start going into the pallets and walking through the folders. About halfway through, maybe like 11 o'clock, we'll take a break. And then we'll come back maybe 15 minutes or 10 minutes later, and we'll do more until lunchtime. And then that's going to look like. But the rest of this time period today is going to be just like diving in and just like kind of getting a feeling for stuff. Again, I think that the pallet system is very intuitive, right? When you see the storage, you see the calls, it kind of makes sense. Obviously, you don't know all the details of you're allowed to do this, you're allowed to do that, whatever. We'll teach that over the day, but I think getting a feeling for what it is to read a pallet and to learn from it is the best way to learn, right?